Okay, here's something to think about. What if a fundamental scientific principle, something we thought we understood for, over 100 years, was actually just a consequence of another, even more basic law?
Right, like uncovering a hidden connection that simplifies everything.
Exactly. And imagine a really tricky puzzle in thermodynamics, one that's been around forever, finally gets solved. And get this, it actually corrects an idea from Albert Einstein himself.
That definitely gets your attention.
It does. So today, we're diving deep into a brand new paper. It tackles this thermodynamics problem that's 120 years old.
Wow, 120 years. That's some serious scientific persistence.
Isn't it? Our source is a really recent publication in the European Physical Journal Plus. It's by Professor Jose Maria Martin Olalla from the University of Seville.
Okay, got it.
And our mission today really is to unpack this whole debate. It's pretty complex. We want to understand why it took so long to solve and really grasp the elegant solution that now links these two principles, things we thought were separate, into one unified idea.
So, streamlining the rule book of the universe, essentially.
That's a great way to put it, helping you get up to speed on a century-old mystery that, just got figured out. So let's get into it.
Let's do it.
All right, first things first. We need to introduce the main players here. We start with the second principle of thermodynamics. This is that core idea, that entropy.
Which people often think of as disorder or maybe the spreading out of energy.
Right, that tendency for entropy in the universe to always increase. That's our foundation.
The bedrock.
Then, building on that, we have Nernst's theorem. You often hear it called the third principle of thermodynamics. And its core idea is that as the temperature gets really, really close to absolute zero, any exchanges of entropy also drop down towards zero.
Okay. And historically, this whole issue popped up back in the early 20th century. Scientists were really digging into how stuff behaves at super low temperatures.
Like really low, near absolute zero, which is minus 273 Celsius. But
that's the one, minus 273 degrees Celsius, a point they were trying to understand and maybe even reach.
And the big name here was Walther Nernst. He really led the charge exploring matter under these extreme conditions. He even got the Nobel Prize in Chemistry back in 1920 for exactly this kind of work.
He did. And his thinking back in 1912 was pretty sharp. He basically argued that you can't actually reach absolute zero. It's fundamentally impossible.
Why, though? What was his reasoning?
Well, his logic went like this. If you could reach absolute zero, you could theoretically build an engine using it as a perfectly cold spot, a coolant.
Okay.
And that kind of engine could turn all the heat put into it directly into work. No waste heat.
A 100% efficient engine.
Exactly. Which would completely violate the second principle of thermodynamics, the one that says entropy always has to increase overall. You can't just destroy entropy like that.
Gotcha. So based on that violation, Nernst stated his theorem that entropy changes go to zero as temperature approaches zero.
Precisely. He used that logical contradiction to establish his theorem.
But then, enter Einstein. This is where it gets really interesting, because he challenged Nernst's argument.
Yeah, this is a fascinating turn. Einstein looked at Nernst's imaginary engine and basically said, hold on, you can't actually build that thing.
It's purely theoretical.
Right. It was a thought experiment, but not physically possible to construct. So Einstein argued if you can't build it, it doesn't pose any real threat to the second law in practice.
Okay, that makes sense from a practical standpoint.
And because of that reasoning, Einstein essentially separated Nernst's theorem from the second principle. He said, okay, this is interesting, this stuff about absolute zero, but it's its own thing. He classified it as a third independent principle.
And that view stuck.
For over a century. It's incredible, really. That interpretation has been the standard textbook understanding until, right now.
Which brings us back to Professor Jose Maria Martin Olalla. His new paper, just out June 13th, 2025, in the European Physical Journal Plus, seems to completely flip that long-held view.
It really does. Martin Olalla's core argument is simple but profound. The third principle isn't independent at all. It actually follows directly from the second principle. They're intrinsically linked.
So how does he prove that? What did Einstein and Nernst miss?
Good question. He points out two crucial nuances that were overlooked in those earlier discussions. First, the actual mathematical framework, the formalism, you might say, of the second law requires that Nernst's imaginary engine must exist, theoretically.
Wait, the second law needs that engine?
Yeah.
Even though you can't build it?
Needs it conceptually, yes.
Yeah.
And here's the second nuance, which is critical. This engine must be virtual.
Okay, virtual. We need to unpack that. What does virtual mean here? It sounds important.
It is crucial. Virtual in this context means the engine is just a theoretical construct within the logic of the second law itself. It doesn't actually consume heat. It doesn't produce any work.
Ah, so it sidesteps Einstein's objection about building it.
Exactly. It's not about a physical machine violating the law. It's about a logical consequence within the law. Because it's virtual, no heat in, no work out, it doesn't actually challenge the second principle in any physical way.
I think I'm getting it. It's like a necessary piece of the mathematical puzzle, not a blueprint for a real device.
You've got it. And when you put those two ideas together, that the second law formally requires this engine, and that this engine must be virtual, something clicks.
So what's the final outcome? What does this unification mean for our understanding?
Well, it means Martin-Alala can derive Nernst's theorem directly from the second principle. He shows that because of this required virtual engine, entropy exchanges must tend to zero as temperature approaches zero.
Which is Nernst's theorem.
Correct. And it also implies that absolute zero itself is inaccessible, all flowing directly from the second law, not standing apart from it. It's a really fundamental unification.
Wow. So it takes two things we thought were separate laws and shows one is just part of the other.
That's the essence of it. It simplifies the foundations.
Does this change how we should think about temperature itself? Because that feels pretty fundamental.
That's another really interesting point Martin-Alala raises. He says a key problem in thermodynamics has always been separating our, feeling of hot and cold, our everyday experience, from the abstract concept of temperature as a physical quantity in equations.
Right, like the difference between saying it feels cold and saying it's 5 degrees Celsius.
Exactly. And historically, in that Nernst-Einstein debate, temperature was often treated more like just an empirical parameter you measure. Absolute zero was maybe visualized as the point where gas pressure or volume would theoretically hit zero, things like that.
Kind of tied to observable properties of matter.
But Martin-Alala's work offers a refinement. He argues that the second principle, when understood through this lens, including the virtual engine, actually gives a much more solid, formal basis for the idea of a natural zero point for temperature.
And this natural zero isn't connected to how cold something feels or gas pressure.
No. It's connected directly to that virtual engine we've been talking about, that conceptual engine required by the second law. This completely changes the way you'd even approach proving Nernst's theorem. It's grounded differently now.
Okay, that's a significant shift in perspective.
It is. And there's one more piece he addresses related to what happens near absolute zero. It's about heat capacities.
Heat capacity. That's like how much energy it takes to warm something up, right?
Basically, yes. How much heat a substance can absorb for a given temperature change. And it was observed, actually, Nernst compiled these observations too, back in 1912, that near absolute zero, the heat capacities of materials tend to drop to zero. They lose their ability to store thermal energy effectively.
So everything sort of freezes up in terms of heat storage.
You could think of it that way. Now, Martin-Alala points out that this observation, the cancellation of heat capacities, seems to be the only general property of matter near absolute zero, that you can't directly link back to the second principle through his new framework.
Ah, so maybe that's the third principle.
Well, here's his take. He argues that the second principle, as he's unified it with Nernst's theorem, already implies that entropy has a unique single value at absolute zero.
Okay.
All the cancellation of specific heats adds, he says, is the information that this unique entropy value is specifically zero.
So it's just pinning a number on something already established by the main theory.
That seems to be his perspective. He actually calls it more like an important appendix than a new principle.
An appendix. That sounds almost dismissive, given it was a key observation by Nernst. What does calling it an appendix really signify here?
I think it really underscores his main point about unification. It suggests that while this zeroing out of heat capacity is important, especially for, practical low-temperature physics, it's not a fundamental law on the same level as the second principle. It's more of a consequence, a detail that emerges from the more fundamental framework.
So it simplifies things.
Right.
You don't need a separate principle of zero heat capacity. It's just part of the package deal that comes with the second law, properly understood.
Yeah, that appears to be the implication. It tidies up the conceptual structure.
Fascinating. Now, this is a big shift in thinking after a century. How does Professor Martin-Alala see this being received? Does he expect immediate acceptance?
He's realistic about it. He actually notes that the academic world tends to have, quote, a great deal of inertia. Change doesn't happen overnight, especially with ideas that have been ingrained for so long.
Understandable. Old habits, even intellectual ones, die hard.
Right. But he hopes that with this paper being published, his demonstration, this new perspective, will start to get more widely known and discussed.
And he mentioned his students were the first to hear about it.
He did, which is quite fitting, isn't it? The next generation learning this unified view from the start.
Absolutely. So just to recap our journey here, we've seen how one really insightful paper might have just solved a puzzle that's been around for 120 years.
A puzzle involving titans like Nernst and Einstein.
Right. And the solution fundamentally redefines how we see the connection between two major laws of thermodynamics. It even sharpens our very concept of temperature at its most fundamental level.
And zooming out, looking at the bigger picture, this whole story is just a fantastic example of how science keeps evolving, isn't it?
Definitely.
Even in fields we think they're totally mapped out, like classical thermodynamics, there's still room for, well, deeper insights, for finding these elegant connections and simplifications that just make our view of the universe a bit clearer, a bit more unified.
And for you listening, hopefully this dive gives you a real glimpse into that process, how foundational science actually moves forward. It shows that, clarity and elegance can eventually emerge, even from really tangled, long-running debates.
Which leaves us with a thought to chew on, perhaps. If an interpretation of a fundamental law, one that stood for over a century and involved figures like Einstein, can be refined and unified like this, well, what other scientific ideas, maybe ones we take for granted, might also be ready for a similar kind of deeper connection?
That's a great question.
Are there other areas where we might be looking at separate principles when really there's an underlying unity waiting to be discovered? How should we approach complex problems, maybe looking first for unification rather than just adding more and more separate rules?